Thank you for watching this video. I am Mr. Ish. We are presenting you a very beneficial video focusing primarily now on Taylor series of the function natural log x centered about a equals 1. You know, when a function is centered with regards to series and expansion about 0, you're looking at Maclaurin series, but here you see a equals 1. What are you looking at here initially? A function is expanded because it has a certain power series representation. You can give it this type of representation: n is equal to 0 and infinity. Remember, just because we have natural log x, it doesn't mean we're gonna not use 0. You know, in general, natural log of 0 is undefined, but when you put it into a power series format, the 0 value becomes a valid input item into that series. What are we putting over here? You know what the formula is. The nth derivative always receiving the a value divided by n factorial x minus a to the power of n. This is x minus a. What do we have here? A equals 1. The most important part, a equals 1. It will fit right over here. It will fit right over here. All of this will become the nth root derivative of that function, always receiving the 1 value. And then you have n factorial. You know, you have this 0 up to infinity. And then you'll have x minus 1 to the power of n. Everything will fit into that scheme. And I promise you, this is not overly complex. What's the next step you want to do? Well, you know you have nth root derivatives. You're going from 0 to infinity. Why don't we set aside 5 derivatives of this function, natural log x? The 0th derivative of natural log x is equal to the original function, which will be natural log x. The first order derivative of natural log x will be 1 over x. The second order derivative, you know you're looking at natural log x, or you just do the derivative of the step before. When you do that, you bring everything and use power rule, you'll have minus 1 over x squared. The third order derivative, you know you use a power rule, you'll have here 2 over x cubed. I'm going up to the fifth. The fourth order derivative will be minus 6 over x to the 4, and the fifth order derivative is going to be a 24 over x to the 5. You know, much of this you can do in your head because it's all basic power rule. Now, what is coming into each of these in terms of your x values? Nothing other than this a. Don't confuse this x for your regular x as you're looking at right over here in terms of like this, your function. You can, but just don't forget that you're looking here at the nth root derivative with the a value feeding in. In all of these instances, the x is being replaced by your a value and 1. This is a good step over here to do. Why? Because it's going to eliminate so much of your confusion from the get-go, because you've already seen what these became. You don't have to see them in a original derivative format ever again. You only have to see what their value input was or what their value equaled to. That's all you have to do. And look what I'm doing. I'm putting the ones over here. Now open up. We're going to go this, your original function, which you know is natural log x. Actually, what is our goal, eventual goal? I want to use approximation using Taylor series to evaluate natural log 1.5. What is the Taylor value in terms of the series of this value, which you can easily do on your calculator, but we're doing here by this method. It's a good approximation method. What is your 0th term? You put everything right over here. Your first order derivative with the 1 coming in, you already have that. You see the benefit of doing this little extra work from the beginning. Natural log of 1 is a 0 divided by 0 factorial multiplied by x minus 1 to the power of 0. This here is my first term, but this, you know, is n equals 0, but I'm telling you in terms of the sequential terms, this right here is first term. Remember, n, let's just say terms is always equal to n plus 1. If you're looking at n equal to 0, it's still your first term because this literally is the first as you're counting your basic count. What's the next item over here? It's going to be this one right here. What's 1? The first order derivative of the a value is equal to just a 1. 1 divided by 1 factorial x minus 1 to the power of 1. That's why I already put the a values here, because I'm reducing work down the road. My next item is a minus. What's minus 1 divided by 1 squared? It's a minus 1. I'm going to have it x minus 1 to the power of 2 divided by 2 factorial. What's my next item? It'll be right here, the third. N equals 3, and you put it right over here. 0, 1, 2, 3. It's a positive 2. X minus 1 to the power of 3 divided by 3 factorial. The next item is this, minus 6 x minus 1 to the power of 4 divided by 4 factorial. And last, it's a positive 24. 24 x minus 1 to the power of 5 divided by 5 factorial. I want to clean it out. You see how everything here started from n equals 0? When you clean it out, this term goes away. You have zeros in here. This 0 right here will zero out everything. When you clean it out, your cleaned out item really, or your cleaned out series, your Taylor series actually starts from here. But for terminology purposes, this right here was your 0 Taylor polynomial. This from here to here was your Taylor polynomial number 1. This is my 0 Taylor polynomial. This is my first Taylor polynomial. This right here is my second Taylor polynomial. From here to here is my third Taylor polynomial, and then up to here is fourth and fifth. You know how it is. Every polynomial is comprised of all the terms from before plus a new term coming from that specific step. If someone asks you to generate the third polynomial for this series, this would be your answer right here after you've cleaned it up. It'll be comprised of this item, this item, this item, and this item. Anyhow, let's clean it out. This right here is a 0. I won't even put a 0. This is an x minus 1 divided by 1. I'm not even putting in the factorial notation anymore. This right here is a minus x minus 1 square over 2. You see how these 1s are showing up? That's my a value, x minus a, x minus 1. A here is equal to 1. Here's my next item. 2 divided by 3 factorial is 2 divided by 6, which is a 1 over 3. X minus 1 to the power of 3 over 3. And very easily a sequence in terms of a rule is coming about. Here I have a 6 divided by 24 factorial, which is a 1 over 4. X minus 1 to the power of 4 divided by 4. And you know what this will be. 24, and that's 120. 120 divided by 24 is a 5. Even if you couldn't do that, you're just seeing 1, 2, 3, 4, 5. It's a 5. And here it's a x minus 1 to the power of 5. When you're looking at all of this, a very good rule comes out. Initially, we're looking here from n equals 0, but now we've eliminated this 0 item. This 0 item is meaningless. Throw it out. We're looking here from n equals 1 up to infinity. Our rule is simple. We have positive minus positive minus positive minus all onwards. You know this will be x minus 1 to the power of 6 divided by 6. My rule will be to create these alternating negative terms. Starting from a positive is a minus 1 to the power of n minus 1. Now, when I'm looking at this part in the numerator, it's always x minus 1 to the power of n divided by n in the denominator, and that right there is my rule. Now, again, just as a rehash, if someone told you to write the 6th Taylor polynomial, this right here is your answer. This entire item here is your 6th Taylor polynomial. You can say that's equal to here your T6x, your 6th Taylor polynomial. If you want, you can put a 0 at the beginning, but that 0 generating from your n equals 0 is meaningless. You can just start from right here, n equals 1. If someone says to write your 4th Taylor polynomial, you know this is what it is. X minus 1 divided by 1 minus x minus 1 whole square divided by 2, and onwards up to right here. So we've done all of this. What do we do now if you want to compute natural log 1.5? Now, what are you thinking this represents here? This here represents an x item here, like your natural log, it's receiving an input. Now that 1.5 you can easily put into these places. When you put that 1.5 in all of these numerators, you'll always have a 0.5 and the rest. When you look at all of these 6 terms, you're looking here at 0.5 over 1 coming from here. Here you're looking at a minus 0.5 square over 2. Here you're looking at a positive 0.5 cube over 3. And you know here you're looking at a minus 0.5 to the power of 4 over 4 plus 0.5 to the power of 5 over 5. And lastly, minus 0.5 to the power of 6. If you were to compute all of this T6 Taylor polynomial, you'd have a good value based on the calculator. 1.5 natural log, I'm getting 0.405465108. And I can put a few digits here. I'm getting 0.405465. That's what I'm getting. I'll do the value here on the side on my calculator, and I'll post you that item. The value that I get using this finite analysis, Taylor series analysis, is 0.4046875. Here I'm getting 0.405, and it's not too far away. We're here accurate up to almost a third digit. You can round this up to 5.405, but you can see if you add more of these n value terms, you'll get even more close to that. But you can see how beneficial this analysis is in terms of computation and comparison to true values. Yes, it's a little more cumbersome, and there are algorithms out there which are perhaps easier, but remember, this is all part of your learning curve and all part of your learning process. You have but one more additional means for approximating values and doing series analysis. What remains over here? We have to analyze this series. Where is our series? Our series is right over here. Now what remains to be done is we have our series which has been generated from the function natural log x centered at a equals 1. It's represented here by means of a power series. We have to analyze it for convergence. And we will do so by the ratio test, a proven method. You know you're going to look at everything here, a n plus 1. You can do that. You'll do n plus 1 in places of n. It'll be minus 1 to the power of n minus 1 plus 1. You have x minus 1 to the power of n plus 1 divided by n plus 1. This n is under all of that. You have absolute value of the a-nth term. You have minus 1 to the power of n minus 1. You have x minus 1 to the power of n over n. All of this is in a dividing, or let's say in a quotient relationship. Open everything up. You're using the properties of exponents. All of this. You can see it's n minus 1 plus 1. This really becomes minus 1 to the power of n. Minus 1 to the power of n. You have x minus 1 to the power of n. X minus 1 to the power of 1 divided by n plus 1. This flips around. Multiplied by n divided by, you can open this up right here as well. Minus 1 to the power of n times minus 1 to the power of minus 1. You see it's minus 1. You multiply these will add and give you that. Times x minus 1 to the power of n. Cancel out your like terms. This cancels out, that cancels out, minus 1 to the power of n cancels out. What remains? You have this x minus 1 in absolute value. You have here minus 1 to the power of minus 1 is no different than a minus 1. You can bring that right here. Limit as n approaches infinity. What do you have here? N divided by n plus 1. This minus can be a little bit irritating. If you see it, you can transfer it right over here if you want. You'll have absolute value x minus 1, limit as n approaches infinity. You can do minus n divided by minus n minus 1. That minus has gone in there and impacted everything. If you do the limit analysis for all of this, you'll still get 1. You're really looking at x minus 1. Absolute value is less than 1. You know that's a convergence for your ratio test. This right here, your radius of convergence is equal to 1. We've already determined that out. Now open this up. You have x minus 1 is less than 1. X minus 1 is greater than minus 1. X is less than 2. X is greater than 0. We're having an interval which is less than 2, but it is greater than 0. We have to see if that's indeed good, or can we fine tune it some more with some sort of equal signs in there. How would you do that? You would look at these endpoints and place them right here into your series and see if you have convergence and or divergence, and then you can fine tune that. You'll take the 0 value and you put it right here in places of x. You have minus 1 to the power of n minus 1. You know we have our series here from n equals 1 up to infinity. We're looking here at 0 minus 1. 0 minus 1 is minus 1 to the power of n divided by n. What about when 2 goes in? You have n equals 1 up to infinity. You have minus 1 to the power of n minus 1. 2 minus 1 is just a 1 to the power of n over n. 1 to the power of n is always just a 1. Think about it. 1 to any number is always just a 1. And this right here can be rewritten as just 1 over n. Let's evaluate this one here because it's easier. You're putting 1 and then 2, 3, 4. We'll just do up to 4 or 5. When you put 1 here in places of n, you'll have here minus 1 to the power of 0, 1 over 1. You'll have just 1. When you put 2 over here, you'll have a minus 1 over 2. When you put 3 over here, you'll have a positive 1 over 3. When you put 4 here, you'll have a minus 1 over 4, and then positive 1 over 5, and then you know you'll have a minus 1 over 6 and onwards. And you can see here you have an alternating series. By means of the alternating series, each succeeding value is less than the preceding and it's tending towards 0. This right here is convergence. So I'm getting here x is less than or equal to 2. When I'm looking at this is a little more tricky. I have minus 1 to the power of n minus 1. I have a minus here. This minus and this minus will work against me. When I'm putting in these n values from 1, 2, 3, 4, when you put here a 1, you'll get a minus 1 over here, and here you'll get a 0 exponent. You'll have a positive 1 times minus 1, you'll have a minus 1. When you put here n value of 2, you're getting here a minus to the power of even, but here you're getting minus to the power of an odd, you'll have a minus 1 over 2. When you put n equals 3, you'll have minus 1 over 3, minus 1 over 4, minus 1 over 5, minus 1 over 6. All of these terms are negative. What is this telling you? Limit as n approaches infinity, this series is tending towards minus infinity. It's not tending towards 0, so it's divergent. I'm seeing this. So what is my interval? It's going to be 0 up to 2, but including 2, and that right there is my interval of convergence. So we've solved it out. This series, which represents a natural log x, this power series, has a radius of convergence of 1. It has an interval of convergence 0, not including 0, but up to 2, but including that 2, and you've seen it. And that right there will bring us to the end of this rather lengthy exercise. but a beneficial one. You've seen how natural log x is derived, and we also evaluated natural log 1.5 using the approximations of the Taylor polynomial 6. We used the Taylor 6th polynomial and we got a good value. If you use a larger n value, a longer polynomial, you get closer to the true value. And thank you for watching this video.